All right. Hello, everyone. First of all, many thanks for giving me the opportunity to present our work here today. And thanks for the conveners of hosting this session online, in addition to the chat session. And first of all, I would also like to thank all my co-authors for their contributions to this work, and the Copernicus for supporting this work. So today I would like to present some work that we did in the last few years on the development of a new European data set, which aimed to support European coastal cities or coastal sectors to adapt to change in extreme sea levels in response to climate change. So yeah, coast are high-risk regions. Over the entire globe, about 110 million people live in regions that are prone to coastal flooding. And it's been estimated that due to sea level rise and climate change, this number may triple if we don't adequately adapt to these changing conditions. Well, large-scale data is an important tool in providing numbers to make decisions about mitigation and as well as adaptation. And that was the main aim of this work. Sort of the initiative came from, we've been for a few years now working on developing these data sets of extreme sea levels globally. And in the last few years, we made major developments in the global modeling of this extreme sea level. So we have a higher accuracy compared to previous data sets. As well as the release of ERA 5 was a major incentive to try to see if we can improve our previous work. And moreover, where before our previous work was confined to the historical period, we wanted to go and take the next step and also project future extreme sea levels. So the main goal of the this project was to develop a consistent data set for Europe, consisting of both tides and storm surges, and for both present day as well as future climate conditions. And next to that, we wanted to provide easy access to this data set, to the Copernicus Climate Data Store. So where before it was quite cumbersome to share data because it's our large files, the Climate Data Store provides the infrastructure to easily share this type of data. So a little bit about the methods. This global modeling is based on the next generation global tide and surge model. It's the third version by now, and it's based on the software called Delft3D Flexible Mesh. And the main advantage of this flexible mesh is that we have a varying spatial resolution. So the model resolution is actually the highest close to the coast. And this makes it computationally very cheap compared to regular gridded models. And in the latest version, the spatial resolution is up to 1.25 kilometers in Europe, which is really a lot higher than any of the other models that are available to model storm surges. And another main innovation of the next generation of this model was that we now can also model tides accurately as well as storm surges, which means we can also include interaction effects between the two, as well as we dynamically implemented sea level rise, which means any changes because of the change in depth will be also affect the tide and the surge. And this is really the only model at the moment that can include this type of interaction. So a little bit more about the scenarios that we simulated. We included the ERA 5V analysis run. So from 1979 to 2017, as well as a baseline climate scenario, which was based on EC Earth, CMAP5 for the globe, and then we nested a DMI HERHAM model for Europe at a higher resolution in it. So Europe actually has a higher meteorological forcing than the rest of the world. And then we used the same setup of climate models to force the future scenarios. Based on RCP 8.5 and 4.5. So what type of output do we produce? Well, we model total water levels as a combination of tides and surges. And in these simulations, we annually update the mean sea level field, which is taken by the IPCC AR5 ensemble. So this then generates a lot of time series of about 200 years in total. And based on these different scenarios, we also compute indicators such as tidal levels, something like a mean high water, but also percentiles and return periods. So in total, this data set was about 20 terabytes. So it's quite a large data set because we have a very high temporal resolution of 10 minutes, which is mostly to capture the tidal frequencies correctly. And the total run time was about 500,000 core hours. So it was quite a big effort to compute all the simulations. This figure shows the output locations that we use. So in total, the model has about 5 million grid cells, which means you cannot save all the data that's simulated in the model. So we developed this set of output locations where we have a set of coastal points, which are indicated in blue, as well as grid points in red. And these grid points are aimed to be used, for example, to nest a local model in. So you could take that as boundary conditions. While the coastal points could be useful for impact analysis and those type of assessments. And as you can already see, we have quite a special focus on Europe, also because that was the aim of the climate data store. So we have a high resolution meteorological forcing there, but also a higher resolution of the hydrodynamic model. And so also the output resolution is higher. So some results. As a first step, we validated the reanalysis run, so the model run based on era 5. And this map shows the bias for the 1 in 10-year water levels, which were compared against observations. And as you can see, there's no clear spatial bias. There seems to be some overestimation in Europe, some underestimation in some tropical regions, which could be linked to underestimation of climate models for tropical cyclones. But overall, there's a good performance, and across all observation points, the mean bias is minus 10 centimeters. So that's pretty good. And then if we compare those results against our previous data sets, so the previous data set that we developed was based on a previous version of the hydrodynamic model, as well as based on era interim rather than era 5, and we have a higher output resolution. And if we compare those results, we see a clear improvement, where the mean absolute error was reduced by 25%, and for about 2/3 of the observation points, we see an improvement in performance. The mean bias was also reduced a bit. So it really shows that these model improvements and this improved meteorological forcing gives a higher accuracy. So this gave us some confidence that we could also use this setup for the climate projections. And here I show you the bias of the historical climate simulation. So this is based on EC Earth with the nested Deerhound model. And it shows that in general, there's a negative bias indicated in red, while in Europe, there's a positive bias. This could be linked to different reasons. It's known that the Deerhound simulation has a bit too many storms in them, so that could influence these results. But there's also some changes in terms of bathymetry in the data set, which could also propagate into this bias estimate. But overall, we see that the global performance is sufficient, and we concluded that we can use this setup as a baseline for the future climate projections. So this is one of the main outcomes of the projects. This map shows the 1 in 10-year water level for 2050 compared to our baseline simulations, where we see a small increase in Europe, a decrease in the Baltic, and some other minor changes. And if we then decompose those contributions, we see that this change is mostly driven by sea level rise, but there's also some change in storminess, especially in the North Sea, which causes these changes. Yeah, just to highlight the importance of including these interaction effects, this map shows the changes in the tidal range in response to sea level rise. This effect is ignored in most of the impact studies, and we usually assume that astronomical tides won't change with climate change. But sea level rise will result in a change in depth, which will also result in a change in tides in some locations. And although the impact will be minor, like up to about 10% of the sea level field, it's still important to include most locations. Also because it can change in like high tides occur twice a day, so it's a much more frequent change rather than a sea level rise change. I'll skip these for the sake of time. Just want to show these box plots which aggregate the change in water levels over Europe. And we see that without sea level rise, there's no consistent change across the European domain, which changes with the mean change varying, being close to zero, although there's some spread for certain locations. While with sea level rise, the mean change is between 20 and 30 centimeters. But if we aggregate change over larger areas, usually they tend to cancel each other out. This is also shown in these two global maps, where on the left side I show the change in the 1 and 10 year return period, including sea level rise, and on the right we excluded the sea level rise signal. And there we see very minor changes, although there seems to be a small decrease in the European part. So part of this project was also to show how this data set could be used by the different coastal sectors. So there were several use cases where people used the data to compute additional climate change indicators and see what would happen under the different climate scenarios. I won't go into that much further. But in the end, this data set will be available at the Climate Data Store soon, hopefully. It's still being uploaded at the moment. And then it will be very easy to fill in this form or use the Python API to download the time series as well as the indicators for the different scenarios. The paper just got published last week by Frontiers in Marine Sciences, and the global return periods based on ERA 5 are already openly available. And hopefully the rest of the data set will become available soon. And I quickly want to touch upon some future research direction, what we see. I think there's many possibilities to use this data, both for more regional studies, as well as use this data to compute, for example, the coastal damages, flood damages due to coastal flooding, those type of things. I think for us, it will be very interesting when ERA 5 will become available from 1950 onwards, because it would really reduce the uncertainty in the extreme value statistics and will become possible to use the longer record to analyze climate variability. And then finally, we have a very large uncertainty because we used a single climate model. So it's fully based on EC Earth. But we recently started a new project where we aim to extend this work using the high-res MIP ensemble.
Sorry,
I'll finish the presentation.
Sorry for that. Thanks very much.